Alright, welcome back, kiddos. And we're continuing our discussion related to bonding. And we, in the last video, discussed electronegativity difference between two bonded atoms and whether or not the bond was classified as ionic or covalent based upon that difference. And it basically came down to this. We said if the electronegativity difference is greater than 1.7, that the atoms are not sharing the electrons very well. They're basically being transferred from one atom to another, so they form what's called an ionic bond. However, if that electronegativity difference is less than 1.7, they're sharing those electrons well enough for that to be considered a covalent bond. So the smaller that electronegativity difference, the better sharing there is. The greater that electronegativity difference, the more of a transfer of electrons there is. And that's how we basically differentiate using electronegativity differences between ionic and covalent bonds. So let me try to illustrate that with sort of a silly little metaphor. Let's pretend that for Christmas one year, two sisters ask for a Barbie doll dream house, and they're twin sisters. They want the same thing. Well, Santa Claus is probably not going to get a Barbie doll dream house for each of those sisters. What he's probably going to do is he is going to ask those sisters to share our Barbie doll dream house. You might be able to imagine that happening. So on Christmas morning, the two young girls come down, they open up their gifts. Yay, Santa Claus got us a Barbie doll dream house. But he put a little note on it that said, you know, we need to share this Barbie doll dream house. And of course, you can imagine that two twin sisters are probably going to share that Barbie doll dream house pretty darn well. There's the sharing of the house. Of course, that's analogous to the sharing of a pair of electrons. However, what if that analogy is changed around a little bit? What if there is a 3-year-old little girl that really wants a Barbie doll dream house and her 5-year-old big sister who would also really like that Barbie doll dream house? And Santa Claus sort of makes the same arrangement with them. Well, okay, we're going to get you one Barbie doll dream house, but you're going to have to share it. Do you think the sharing goes on as well between these two sisters as it did between these two sisters? Probably not. The big sister is probably going to get her way more often. She's the one that's going to be able to play with the Barbie doll dream house whenever she wants, and the little sister, the poor little thing, is probably going to get it whenever the big sister isn't around. So there's not equal sharing of the Barbie doll dream house. Now, that's sort of analogous to having a very electronegative atom like fluorine sharing a pair of electrons with an atom that's not very electronegative, maybe something like potassium. And so the electron, or Barbie doll dream house in this case, is basically transferred to the one that's more electronegative. I hope that helps you out in understanding electronegativity differences in classifying bonds as ionic or covalent. And let's go back to drawing some Lewis structures, kiddos. We're going to be doing a lot of this in the next couple of videos, and you are going to get pretty good at it. In fact, it might be one of the more fun things you do all year. Let's draw the Lewis structure for chlorine gas, Cl2. So let's first find chlorine gas in the periodic table, or chlorine atoms on the periodic table. Let's see what group they're in. Here's chlorine right here. Do you see they're in group 17? Of course, that tells you right away they have 7 valence electrons each. But we could do the end of their configuration to verify that. Wouldn't it be neon, 3s2, 3p5, and of course that gives you 7 valence electrons. So if I have 2 chlorine atoms and each of them have 7 valence electrons, I will have 14 valence electrons to use in my Lewis structure. Now remember, when we draw Lewis structures, those atoms share a pair of electrons. So I'm going to put a pair of electrons between the 2 chlorine atoms, and that would be my covalent bond. That would be my shared pair right there. Well, what am I going to do with the other 12 valence electrons? Well, let's go ahead and place those around each chlorine atom as unshared pairs, but complete their octet. So if I put 6 more around this chlorine and 6 more around this chlorine, I end up giving each chlorine atom, for at least part of the time, 8 electrons. Doesn't that chlorine atom have 8 electrons around it part of the time? 4 pairs? It's a stable configuration. And doesn't this chlorine atom have, for part of the time, 8 electrons around it. Yeah, it has an octet. They both have a noble gas configuration. So that would be my Lewis structure for chlorine gas, Cl2. Now what shape would that molecule have? Well, that's pretty easy to describe in this case. There's only 2 atoms, and whenever 2 atoms are bonded to each other, the shape is always going to be linear. It can't be anything else. So all diatomic molecules, those are molecules made up of 2 atoms, will always have a linear shape. Sometimes we call that molecular geometry. Whenever there are 2 atoms bonded to each other, they don't have any other choice but to be linear. Well, how about its polarity? Well, let's use our little Barbie doll dream house analogy to help us figure this out. We have a sister here and a sister here, and they're sharing that Barbie doll dream house. Since they're the same atom, aren't they going to share it pretty well? Yeah, they're the same size, the same electronegativity values, so that means that this molecule will not be polar. There is complete equal sharing of that pair of electrons. The electronegativity difference is 0, so this would be a nonpolar molecule. Now, does that mean that all diatomic molecules have the same polarity? Are all of them nonpolar? No, think about this. We did this on the previous page. Remember when we had HF and we drew that Lewis structure. F is much more electronegative than hydrogen, and so that molecule is polar. Using our Barbie doll dream house analogy, H would be my little sister right here, and F would be the big sister, and she would get that shared pair of that Barbie doll dream house more often. So not all diatomic molecules are polar. Not all diatomic molecules are nonpolar. So when I ask, do they have the same polarity? No, they don't. We have to draw the Lewis structure, figure out the electronegativity differences, if there is one, and then we can determine their polarity. Well, what about molecules with more than 2 atoms? Let's see, so far we've drawn the Lewis structure for H2, HF, and Cl2, haven't we? All of those Lewis structures have only 2 atoms in them. Well, what if we have structures or molecules with more than 2 atoms? There are lots of those. So this is how we do this. For a molecule with more than 2 atoms, we need to assume that nature tends to make symmetrical molecules. And therefore, one of those atoms has to be in the center of the molecule. In this case, it's obvious that hydrogen cannot be in the center. Well, I haven't given you an example yet. The example would be H2O. So why can hydrogen not be in the center? Well, let's try to draw the Lewis structure with hydrogen in the center. If I put H in the center, and O on one side and H on the other, and I put a pair here between this hydrogen and the other hydrogen, and a pair here between hydrogen and oxygen, hopefully you can see right away that that's not possible for that hydrogen. How many valence electrons can hydrogen have? That's right, it can only have 2. So hydrogen can only make 1 bond. So hydrogen can never be in the center of a molecule. Okay, it needs to be on one of the ends. So, if it's not obvious what the central atom is, a good rule, and it's not always the case, is that atoms with the highest electronegativity end up in the center. It's not always true, but it's a good rule of thumb. The other atoms are symmetrically placed around the central atom. So, if I were to draw the Lewis structure for H2O, that molecule has 3 atoms in it, 2 hydrogens and an oxygen. Maybe I could put oxygen in the center, a hydrogen on one side, and a hydrogen on the other. Then this oxygen could share a pair with that hydrogen. This oxygen could share a pair with that hydrogen, and the other pairs could be placed around oxygen to complete its octet. Let's see if that works. How many valence electrons do I have available in the molecule H2O? Well, let's take a look at the periodic table. Hydrogen, kiddos, is in group 1. It has 1 valence electron. Oxygen is in group 16. It has 6 valence electrons. So if I have 2 hydrogens, each with 1 valence, that gives me 2 valence, and an oxygen with 6 valence, Doesn't that give me 8 valence electrons to work with in my Lewis structure? And if you take a look, that's exactly what I used. And you will notice that oxygen has an octet, 4 pairs of electrons around it, part of the time. This hydrogen has a pair of electrons around it. And for hydrogen, remember, that's the noble gas configuration of helium with a pair of electrons, and it is stable. And so does that hydrogen. So each atom is stable by being able to share those electrons. So there are some rules for drawing Lewis structures that we're going to use quite a bit now. And once again, you're going to get pretty darn good at this after we do a few examples. First, we'll count the total valence electrons available, like we just did up here. Then we're going to connect each atom with a single bond or pair of electrons, like we did up here. And then we're going to place the remaining electrons around the atoms as non-bonding pairs. Now we might need to use something called double or triple bonds, which you'll see in just a bit, because sometimes atoms need to share 2 pairs, or maybe they need to share 3 pairs in order to complete their octet. And we'll get to that soon enough. Okay? Well, let's do a few more before we wrap this video up just for practice. So for water, H2O, we had 2 hydrogens, each having 1 valence. So 2 valence from my hydrogens. 1 oxygen, which has 6 valence. So we could have 8 valence in my Lewis structure. We put oxygen in the middle and a hydrogen on each side. That looks pretty symmetrical, doesn't it? We'll put a pair between oxygen and hydrogen on each side, and then we'll give the other 2 pairs to oxygen to complete the octet. So now the question becomes, what is the shape of this molecule? Well, I think we have 2 choices here. One of my shapes could be a nice linear shape. There could be an oxygen in the middle and the hydrogen on either side and have a nice linear molecule. However, another option is we could end up with this type of shape where the oxygen's in the middle and the hydrogens are in what we call a bent position. So this would be called linear, all in a straight line. This would be called bent. Now, what is the correct shape and the correct polarity? Well, I'm going to leave you in suspense. We're going to come back to this question in just a bit. For right now, we're just going to practice drawing Lewis structures. Okay? You now take a moment and try to draw the Lewis structure for ammonia, NH3, and see what you come up with. Go ahead and pause the video and try it now. Okay, welcome back. Let's figure out our total valence electrons. There's 1 nitrogen, and nitrogen is right here, folks. It's in group 15 of the periodic table. It has 5 valence electrons. And we have 3 hydrogens, and we know that they each have 1 valence electron. So we have 5 plus 3. Looks like we have 8 electrons to worry about. Let's put nitrogen in the middle. We know that hydrogen can't be in the middle. And on 3 of the 4 sides, we'll stick our hydrogens. Now you'll notice that I've used lines here instead of dots. I could have drawn dots like this, and that would have been completely acceptable. But it's also acceptable to use a line connecting the atoms like this to represent 2 electrons or a shared pair. Either way is fine. Now, if you take a look, I've used 2, 4, 6 electrons. If I put 2 more on that nitrogen, or I'm using my dots, 2 more on this nitrogen, you will notice, kiddos, that nitrogen has an octet here, and if you did it this way, it has an octet there, and each hydrogen has a pair around it, which is stable for the hydrogen atom. So that would be a good Lewis structure for ammonia, NH3. Now, what shape would it have? Let's redraw it because it's getting a little bit claustrophobic up there. What shape would this guy have? Well, they could be flat and they could be placed on a plane, and we could end up with something like this with the nitrogen in the middle. We call this trigonal planar. But maybe the nitrogen's up top and those hydrogens are forced down into a pyramid type of shape. If we end up with this shape over here, we call this trigonal, but instead of planar, we call it a pyramid. So it's going to be one of those two shapes, and once again I'm going to leave you in suspense. We'll figure out the shape here in just a bit. Alright, let's draw one more Lewis structure before we call it quits on this video. Why don't you take a minute and draw the Lewis structure for methane, CH4. Then come back to the video and see how you did. Alright, welcome back. We have 1 carbon and 4 hydrogens. We know each hydrogen has 1 valence. We've used hydrogen a bunch today. Carbon, however, let's find carbon. Here's carbon. It's in group 14 of the periodic table. It has 4 valence electrons. So it looks like once again I'm going to have 8 valence electrons in my Lewis structure. Put carbon in the middle. I'm going to go ahead and use lines, kiddos. Remember, each line represents 2 dots. And I'm finished. Yeah, take a look. If you take a look at the Lewis structure, the carbon has 4 pairs around it, and each hydrogen has 1 pair around it. And so every atom is stable so long as they share those electrons. So let's redraw this to investigate the shape. So I could make a nice little cross like I have right over here. And if it ends up like that, we call this guy square, for obvious reasons, planar. That means it's a flat square. However, we could end up with the carbon in the middle and a hydrogen poking up, these two coming out of the paper, and this one going back into the paper. And that is called tetrahedral. So the shape of methane is going to be one of those 2 shapes, and we'll figure out what those are in the next video. Alright, thanks for paying attention. We'll also practice drawing lots more Lewis structures too very soon. See you soon. Bye-bye.